Hello everyone, my name is Zhanyuan. The topic of our group is accurate concrete strength prediction based on two-stage ensemble machine learning. Here is the motivation of our group. It is known that strength is of special importance in concrete production. However, the complex relationship between the strength and input factors, such as the fraction of ingredients, remain unclear. Currently, the researchers are trying to use data-driven machine learning techniques, such as random forests, artificial neural network, to provide some new possibilities to find out the relationship between the strength and the factors. Here is the data we use to create our model. Our data is from a real data set collected in concrete production. Different amount of data are available for 12 mixed inputs, and we use the 28-day strength as output. After cleaning, there are 7,441 data points in total available for our analysis. The variables we used in the model and their explanation are shown in the table above.
Now we will introduce the methodology used in our research. These are the abbreviations of the machine learning models used in our algorithm. In our presentation later, we will elaborate further on the use of these models. In order to accurately predict concrete strength using our dataset, we developed a two-stage model, combining different regression and classification methods to optimize the result. We use a first stacking model to create a new variable, early or late indicator, which is used alongside other existing predictors to predict the 28 strength of the concrete in the second stacking model. This is a brief summary of our method, and we will go on to introduce the two stacked models in a more detail. So before talking about the first stacking model, I would like to introduce the concept of early and late concrete. The early and late concrete is defined based on the relationship between its 7-day strength and the 28-day strength. We first build a simple linear regression using 7-day strength as x and 28-day strength as y. The least square regression line splits the 2D plane into two portions. We define the data points above the regression line as late and those below as early. Practically speaking, while concrete strength stabilizes after 28 days, some develop full strength earlier on, and those are early concrete, and while others are late, and we call them late concrete. Note that the classification becomes less reliable as the distance between the data points and the regression line decreases. Thus, we remove those potentially confounding points to maximize the first stage performance. Our first stacking model, whose aim is to differentiate between early and late concrete samples, implements 6 machine learning models that are applied on the data set of the removal of the confounding data points to maximize prediction accuracy. To get the best result of our classification stage, we applied a few of the reliable methods in data science, including linear models such as linear discriminant analysis and generalized linear model, and non-parametric models such as k-nearest neighbors. We've also employed tree-based decision algorithms such as random forest and gradient boosting, as well as the neural network model. The prediction result of these models are then aggregated using the support vector machine algorithms to classify early and late concrete. So this is the first stacking model in our algorithm, and my groupmate Ollie will then introduce the second stacking model.
We then introduce the final prediction of the first stage model as a new binary variable. With 6 original raw inputs and 1 binary variable, the second stage model aims to create a final prediction of the 28 days concrete strength. Using a similar structure as the first stage model, we aggregate the strength predictions from base models, such as generalized additive model, random forest, gradient boosting, and support vector machine using lasso. We chose lasso because it provides a linear combination of each of the predictions with the coefficients representing how much each base prediction is weighted into a final prediction. By goggling the coefficient, we select only those informative base models. Finally, using the second stage stacked regression model, we obtain the final predicted 28-day strength.
The plot on the left demonstrates the classification result after applying the first stage stacking model. As you can observe, the model successfully classifies highly early or highly late concrete. The prediction accuracy decreases as the distance between the data point and our threshold line decreases. This is also demonstrated by the plot on the right. This plot groups data points based on the relationship between its 28-day strength and 7-day strength. It shows that as the data gets closer to the regression line, which is indicated by the red line in the figure, the percentage of error, which is indicated by the purple bars, increases. To demonstrate our first stage stacking model superiority, we replicated the exact same classification problem using extreme gradient boosting. Our stacking model improves classification accuracy, sensitivity, specificity, and the F1 score. Next, we will demonstrate the second stage stacking results. Before we apply the stacking algorithm, we set the baseline by using the random forest model to directly predict 28-day strength with the 6 raw input variables. We use the default parameters of 500 trees and repeat the process 100 times. The plot on the left shows the R-square distribution as well as the mean R-square over 100 repeated tests. The mean R-square is 0.6. Next, we will attempt 4 variations of the stacking model. Our goal is to first validate our stacking regression model's better performance compared to the baseline random forest model. 2, investigate which second layer algorithm yields the best perform results. And finally, testing whether or not including the early-late indicator benefits our strength prediction.
Here is the result of our stacked model. So for all the trials are finished based on a 10-fold cross-validation. For the figure on the left, it is the testing R-square for all of the 10 folds. And for the table on the right, it shows the average testing R-square for the 4 models. As in the table, we could observe that the random forest, using random forest as stacked model in the second step, will underperform the case when we are using lasso as the stacked model. And also from the table, we could see that the indicator provides useful information in predicting 28-day strength, as of the models with indicator outperforms the models without indicators. Here, we plot the predicted 28-day strength versus the actual 28-day strength in the plot. Then we fit a line between them. We find the overall R-square value equal to 0.766, which means that 76.6% of the actual strength variance could be explained by our model. Here is the conclusion of our models. First, in general, the two-step stacking model outperforms the baseline model using random forest as a regressor. Second, for two-step models, ensembling more regressor in the first layer will improve the performance of the model from our trial. However, simpler, more explainable, and parametric model serves better at the second layer. The reason behind it is because for the first layer, we are using 28-day strength as the output. Therefore, the second layer should try to pick out which model performs the best in the first layer. Therefore, using a parametric model such as lasso, we could easily find out the best model in the first layer by simply reading their coefficients. Third, the formation speed of the concrete contributes to the prediction of the final concrete strength, which means that the early-late indicator is a useful indicator. Here, we would like to thank Professor Mathieu Bauchy, Dr. Yu Song, and Boya Ouyang for their support and advice throughout the project.